yesterday, giving some examples, we found upper bounds for Tarski numbers, and also in some cases, we wrote paradoxical decompositions for Tarski numbers. And in the end of the class, I gave some examples, and I hope you try to find an upper bound for the Tarski number. Of course, it was C6, but C4 is right. And I myself wrote the diagram that we need for upper bound for the Tarski number, and I see that the upper bound for Tarski number in this case is 10, using this special diagram. In our examples, in special cases, we found upper bound for Tarski numbers, but we did not give any strategy for the general case. Today, I'm going to give such a strategy. Before that, I need some definitions and some notations, and after that, I will give the theorem that I want to say. Let me define a new type of configurations, of paradoxical decompositions. I say that G, a discrete group G, admits a new paradoxical decomposition. It's somehow different from the other kinds of paradoxical decomposition. G admits a new paradoxical decomposition. If G has a partition, has a finite partition, like this, a finite partition for G, with this property, and where there exist some subclasses of A, C1 to Cn, and D1 to Dn of A, such that there are G1 to Gn and A, the disjoint union of A, where A belongs to Ci, is Gi, union of A's, where A belongs to Gi, and it happens for every I. And another condition is that for each A in A, the number of I's where A belongs to Ci is strictly less than the number of I's where A belongs to Di. This is the cardinal number of this set. It's finite, and the other is the cardinal number of I's that A belongs to Di. With these properties, we can see that, again, G is non-amenable if and only if admits a new paradoxical decomposition. In fact, the main difference here with the other kind of decompositions is that these sets need not be disjoint. The main point is that these are not necessarily disjoint. So I want to give a very short proof for the theorem. After that, I continue. Okay, if G is non-amenable, then G admits a complete paradoxical decomposition. And I only give a very short sketch of the proof. G is something like this: AI, Bj, and GIAI, and at the same time is the union, disjoint union of HJ, EJ. It means that A is equidecomposable to G, and G has two parts, A and B again is equidecomposable with G. So it can be divided into some parts. Some of them makes A, some the others make the other one makes make G. Therefore, these sets make the I's, and these parts, it just needs some writing, some intersections, some unions, and it's not difficult, but take some time. And these sets, these parts that by translation go here, makes the CIs. And so you see that the difference between DI and AI make G completely, and it is this condition. And the other is the translation and the equidecomposability of A and B and G. So this is the sketch of the proof of this direction, and for the other direction, it's easier. If G admits a new paradoxical decomposition, then we have such a thing. And by this condition, we can see that mu of G, mu is the, I suppose that G is amenable and admits a new paradoxical decomposition. So there is a left invariant, finitely additive probability measure. It means that it is 1, and by our assumption, it is the sum of mu of A, where A is a set in our partition. But this is by this condition. This is strictly less than mu of A, I from 1 to n, and A belongs to the I, minus mu of A, where A belongs to Ci, and I from 1 to n. But these two, because of left invariance of mu, are the same, and it is 0. And it is a contradiction. Yeah, 1 is less than 0, and not possible. So this condition is again admitting new paradoxical decomposition is again equivalent to the non-amenability of the group. But the main challenge of us is that how to find the Tarski number using this kind of paradoxical decomposition, because for the Tarski number of group, we need a complete paradoxical decomposition, or at least disjointness of these sets are very important for us. In our assumption, the sets are not necessarily disjoint, and we try to solve this problem in the area of configurations, and with the sense of configuration that I try to find the Tarski numbers and paradoxical decompositions and so on. Okay. There is a very famous theorem in the convex geometry. It is the theorem of Gordon. Gordon's theorem. It says that if AX equals to 0 is a homogeneous system of equations, finite system of equations, linear equations, it means that A is in the n type, n times m of R. Exactly one of the following statements happen. The first says that AX equals to 0 has non-negative, non-zero solution this is what we want. And the second says that there is y, a vector, in Rn such that once y transpose A has a strictly positive entries. Each entry in this vector is strictly positive. Okay? I want to use Gordon's theorem to find paradoxical decomposition and of course the upper one for the Tarski number of my group. Now, so let as a theorem let's write our system of equations, the system of configuration equations like this. AX is BX. I remind the definition, it was sum of FC's is equal to this. These are unknown variables. C J is I, and this one says CK, for example, is I. Or you can, instead of K, write 0, and again, we have all these equations. So I have some purpose to write this in this case. So I call FC X, and after that I write this in this case. A and B have entries only in 0 and 1. So A and B are 0, 1 matrices. And X is the vector of our unknown variables. So I can write, for example, A as A1 to AK, suitable dimension, and B, it depends on the number of I's and J's and the number of configurations, and B, something like this. These are the rows of A and these are the rows of B. And if it admits no non-zero solution, that admits no normalized or no non-negative non-zero solution, then by Gordon's theorem, we have there is a y, and because of the kind of A and B, which are 0, 1 matrices, you can choose your y in something like y1, y k, in n to the k, not in R. They can be chosen positive and of course integers, positive integers, such that yt b minus a has positive entries by Gordon's theorem. And what does it mean? Using the configuration equations, it means that it doesn't need any proof, because I write the proof in the same. It's better write as a remark, not a theorem. Okay, and it means that there are subsets C1 to Ct, D1 to Dt, subsets of this set x0 of C, where C is a configuration, and with the suitable property that I need, such that I should mention, I write, I'm using this fact that Aij, the notation that I introduced yesterday, it was the set of C's where C belongs to x0 of C, xj of C is a subset of AI. I'm using this fact and the fact that this notation and the fact that Aj, let me write it again. We have this disjoint union of A of x0 of C, where C belongs to Aij, is in fact Gj minus 1 Gk, the union of x0 of C, where C is a member of Aik. It is routine to see that this is happening, that for each C, the number of i's where x0 of C belongs to Ci is by this condition. We have such a thing that we are willing to have, and the number of i's that x0 of C belongs to Di. So we have a new paradoxical decomposition. Let us review this again once more. We are using configuration equations and want to find paradoxical decomposition. By Gordon's theorem, we have a new paradoxical decomposition, but still we don't have a complete paradoxical decomposition. We need this one and the Tarski number of them, or at least an upper one for the Tarski number. So the main challenge is to find a complete paradoxical decomposition and therefore Tarski number using new paradoxical decompositions. And what did we do in our examples yesterday was exactly solving this problem. In all examples, we have something like this. For example, A1, it went to B1, A2 to B2, and for example, AP to BP. And these sets were not disjoint in general. So we find the intersection between these two sets here, and the intersection between A3, A2, and A1, the intersection of them into these two sets, and again, so on. And after that, we make disjoint subsets, and the paradoxical decomposition is written. Now I want to give a strategy in general to find the paradoxical decomposition. I need a condition on my equations to have such a decomposition. So I again need another notation. I write Eij for the matrix which have 1 in the position ij, the row I and the column j, and the other is 0. And I write T maybe with dimension n, the identity matrix in this dimension, plus Eij, where I is less than j, and this is less than. It is such matrix. It is a lower triangular matrix, which entries are under the diagonal are 1 and the others are 0. I use this notation to define my condition. I say that a system of equations, of course, a finite linear system of equations, ax minus bx is 0, is normal. This is the name I gave to this condition, this definition. A system of equations like this, which is homogeneous, is normal if the sum of bi minus ai has strictly positive entries, okay? And this condition, T b minus a minus a plus, I explained this vector, this is plus, has entries strictly greater than -1 or equal, no problem. So I call this system a normal system. By this condition, the system has no non-negative, non-zero solution. I say normalized solution. And by this condition, I can make my new paradoxical decomposition into the complete paradoxical decomposition. And after that, I can write the this kind of paradoxical decomposition and also find the upper bound for the Tarski number of G. In the case that all of them are 1, in the case, so Tarski number of G is less than or equal L minus 1 2 to the P, and I think plus 1, I write it complete. Let me see. Okay. It is minus 1 again, not plus 1. And this is, yeah, it's correct. Okay, I would say this, but this is a normal condition for a system. I want to write it for my equation. If G is a discrete group, and if G is a discrete group, and EQ of G and E, you know, G and E is a configuration pair, contains a subsystem which is normal, then G admits complete paradoxical decomposition and in the case I explained this, and in the case that I write this the subsystem something like this, bx minus ax 0 are all 1. It means that every entry of this vector is 1. Then in this case, okay, because I explained it, I erase the parentheses. We have such a upper bound. I rewrite it again. 1, 2 to the P minus 1, where L is the number of configurations and P is the number of equations. In the subsystem. Okay, of course, this upper bound is not very accurate, and I don't claim that it's the best upper bound, but my point is that I can find an upper bound for the Tarski number of group using only configuration equations. You may find an upper bound or write some paradoxical decomposition using Cayley graphs and Hall marriage theorem and something that are very famous and are usual to use. But for me, it was important to find in this course, it's important to find upper bound for the Tarski number using only configuration equations. In the systems that we used yesterday, all of them have this condition. All of them had subsystems that were normal. We didn't point out, but we knew that there was such a thing. And for the first example in the beginning of the class, I remind this again. It was 1, 3, 1, 2, 3, 1, 2, 3, 5, and I had 1, 2, 4, and they went to 1, 3, 5. Again 1, 3, 5, went to 1, 2, 3, 4, and the last one said C3 is going to 1, 2, 3, 4, 1, 2, 3, 4, and 6. So, it means that the intersection between these two is here, and the intersection between these three, it is in BIs, and so on. This condition, the condition of normalness, says that T B minus A minus A plus, and I didn't explain it, it must have entries greater or equal to -1. And what does it mean? A plus, by A plus, I mean this matrix. A2, A3, it has a permutation here, a cycle, B, A n minus an, and the last one is A1. This is A plus, and it means that, for example, B1 contains, call these sets DIs, D1, D2, D3, so on up to the end. And it means that the set of x0s where C belongs to, for example, DI, D1, contains the intersection between x0 of C, where C belongs to A1 and A2, in the intersection of these two. And so we could omit the intersection and make them disjoint, and after that write the paradoxical decompositions. As you see in the beginning of the class, I wrote this. But the proof of the theorem, the general case, is not very easy. It has not very complicated, but very long proof. You can see the proof in my paper, a constructive way to compute the Tarski number of groups. In 2008. Okay. Now we can go to other properties of configurations. If there is no example, if there is no question, I can go on. Okay. All right. The other properties of configurations. Again, I want to go back to the definition of configurations. C was a configuration corresponding to G and E. If there was an x0 in G such that Gj x0 belongs to E C. The set of all configuration corresponding to G and E is denoted by this, and the set of all configuration of a group is denoted by G. The set of all, where G and E is a configuration pair. Okay. There is a very easy theorem here saying that if H is a subgroup of G, then all configurations of H, this set is a subset of the configurations of G. It is not difficult to see. It's only enough to write H, G as a union of right cosets of H. And then I explained something like this yesterday. You can see this. So configuration of H is a subset of configuration of G. And another thing that is also very easy to see, that if N is a normal subgroup of G, then configuration of G over N is a subset of configuration set of G. Okay. And there's a nice problem here, nice theorem. It says that if G1 and G2 are two discrete groups, and if configuration set of G1 is a subset of the configuration set of G2, then we can conclude that the Tarski number of G2 is not greater than the Tarski number of G1. I give a short proof for this. After that, we have a known result using these two. Now, for the proof, it may not be very easy to see or very routine, but it's not very difficult. It's enough to look at this, the definition very carefully. I want to prove this, so let G2 is paradoxical. No, and even better. If for example, if G1 is amenable, if G2 is amenable, then every configuration equation of G1, G2 has normalized solution, but every configuration equation for G2 is also a configuration equation for G1, and therefore that one is amenable too. Let's postpone this first. I prove this for non-amenable group. After that, I explain it for amenable group as well. Let G1 is paradoxical. It means that this group is not amenable. Okay. Let G1 is paradoxical. It means that there is a complete paradoxical decomposition for G1. There are such subsets, disjoint subsets, union of AI and union of BJs make G, and at the same time we have the union of GI AI and the union of HJ BJ are also the whole of G, the whole G, G1. Look at this string of elements of G1, G1 to Gn, and H1 to Hn. Okay. For the convenience, I can name them in the same letters. For example, this one is AI, and let's write the common letters for them. It's easier to see them. It is, and this one. G1 is paradoxical, so there are some subsets. I from 1 to n, and EI again. This time I from n plus 1 to n plus 1, n plus m. And here GI AI, from 1 to n. And again GI AI, I from 1 plus n to n plus m. This is better. There's no difference to for the definition, but for writing, it's easier to write. G1 to n plus m, and define this notation. I want to use this notation. BIK is the set of configurations in CON of G and E. This G and E is this partition, E1 to En plus M. So BIK be the set of all configurations in configuration of G and E, such that X0 of C is a subset of EI, and Xi of C is a subset of EK. Okay, to make this short, I only write the sentence that I needed. After writing some unions, we see that K from 1 to n plus m is joint union of x0 of c, I from 1 to n is is EI. Because I'm omitting the proof, I need to be accurate. Okay, and yeah, K from 1 to m, n plus m, and C belongs to BIK, right? Okay, we have EI, and I from 1 to n is joint union of C in BKI, GI, x0 of C, it is EK. Okay, we haven't used the condition that we have in the sentence of theorem. I just write the configurations corresponding to this G and this E, and after that we see, in general, we have such a thing. Whenever G is paradoxical, we have something. Now, I want to use the condition. Configuration of G1 is a subset of configuration of G2. Therefore, because CON of G and E for this specific choice is a configuration in G1, therefore it's a configuration in G2 as well. And therefore we have, there is a, something like this, G prime, G1 prime to N plus M prime, and a partition E1 to En plus M. These two are for G2, such that they are the same, such that configurations, some n plus 1 tuples, n plus m plus 1 tuples, G and E, are exactly configuration of G prime and E prime. This one is for G1 and this one is for G2, but the same tuples. There are only some tuple of numbers, and it doesn't depend the construction and the shape of the groups, group G1 and G2, because these are only some tuples of numbers. And after that, we see that, we can see that I just, because I know writing is completely maybe boring, I don't want to write it completely. You can see the proof in some papers. In a paper. In the end, I will give the references. Now, after writing this, you can see that something like this happened again for group G2. And I don't want to write it again. I just make some primes here. Exactly the same equations happens for G2. Because they have the same set of configurations. Okay, now you can write it, and let me write again. G2, I know this is a partition for G2. Therefore, it is the disjoint union of K from 1 to N plus M, x0 of C, which makes EKs. And on the other hand, very easily you can write it and see that again I from 1 to m gi to m giai is g2, sorry, ai prime ai prime is g2, and again I from 1 plus n to n plus m gi prime ai prime is again g2. It means that we have a paradoxical decomposition with the same pieces, the same number of pieces for g2. It means that the Tarski number of g2 is less than the Tarski number of g1. Okay, the Tarski number of g2 is less than the Tarski number of g1, and we're done. Okay, it's for non-amenable groups. If G is non-amenable, it's paradoxical. If G2 is G1 is non-amenable, G1 was paradoxical, and after that we saw that G2 is paradoxical too, and the Tarski number of G2 is less than the Tarski number of G1. If G2 is amenable, okay, what we conclude? Let's write another theorem, and I explain this theorem. Let they have the same set of configurations. Let configuration of G1 is exactly the set of configurations of G2. And we can see the amenable case. If this happened, then the Tarski number of G1 is exactly the Tarski number of G2. And the proof is trivial because one inequality is proved here, and the other proved the equality equations. For the proof, since configuration by the previous, in the case that G1 is non-amenable, G1 and G2 are non-amenable. By the previous theorem, the Tarski number of G1 is exactly the Tarski number of G2. Each one is less or equal than the other, so they are equal. And if G1 is amenable, because they have the same set of configurations, they have the same set, they have the same equations, configuration equations. Therefore, if one admits a normalized solution, one system, the other also admits the normalized solution. Therefore, if G is amenable, then G2 is amenable as well. Okay, because they have the same set of configuration and the same system of configuration equations. It says that the Tarski number of G1 is infinity. For the case of amenable, we defined it infinity, and that one says that the Tarski number of G2 is infinity as well. So in this case, because it's if and only if, we have the Tarski number of G1 is exactly the Tarski number of G2. And for the one direction only, we see that the Tarski number of G2 is less than the Tarski number of G1. And that's it. Okay. So we have Tarski numbers for group with the same set of configurations. Okay. There are some other properties for Tarski numbers, for configuration of groups, and I write them here. Let's restrict ourselves to the case of finitely generated groups, not an arbitrary group. Let G be a finitely generated group. Be a finitely generated group. And G be a generator for G. And let also E is a finite partition as before, E1 to EM, a finite partition for G. And the definition is the same, but I want to use another notation. We say that in this case, we write configuration of G and E belongs to CON, some star I put here. Configuration S star of G. It means that we emphasize that G is a generating set, a finite generating set for the group. There are many beautiful results after adding this condition to our definition. For example, theorem, if G is a finitely generated set group, finitely generated group, and G2 is also a finitely generated group, and they have the same set of such configurations, then we have something. Then 1 f of G1, I will explain this, is f of G2, whereby this I mean that for each normal subgroup of G1, which has a finite index in G1, there exists a normal subgroup for G2, like for example F, normal subgroup of G2, such that G1 over N is isomorphic to G2 over F. And another result, number 2, says that if there is a number 2, if there is a semi-group law, there is a semi-group law that every element of, for example, G1 satisfies in that law, then so is, so are, yeah, so is every element of G2. If one of them satisfies this condition, the other one is also satisfies the condition. By a semi-group law, I mean something in a free semi-group. For example, something like x1 alpha 1 to xn alpha n is equal to y1 beta 1 to ym beta m, with this condition that alpha i's and beta j's are all positives, positive, not negative. It is a semi-group law. For example, as a result, we see that, for example, this is a semi-group law. AB is BA. So if G1 is amenable, if they have the same set of configurations, CON of G1 is CON of G2, of course, by a star. Is C1, this has a star. CON of G1 a star is CON of G2 a star. If they have the same configurations, then G1 is abelian if and only if G2 is amenable, is abelian. Because this semi-group is satisfied for every element of G1, then it automatically happens for G2, and therefore G1 is amenable if and only if G2 is amenable. Okay, and we can have a break now, and after that we continue. Okay, from now to the end of our talk, this session, I suppose that every group that we are dealing with are groups, are finitely generated groups. Okay, let me remind some definition that we had before. We said that a group G is FC group, is FC if every element of G has only finitely many conjugates. And in this case, for finitely generated groups, G is FC if and only if G over Z of G is finite, is a finite group, and G prime is also finite. Okay, and let me remind some theorem. Says that if f of G1 is f of G2, I mean that they have the same set of finite quotients, isomorphic finite quotients. So, and G prime 1 and G prime 2 are finite. Then G1 times Z is isomorphic to G2 times Z. Now I want to prove this theorem. If G is a finitely generated nilpotent FC group, and configuration star of G1 is the same as G2, then G2 is a nilpotent FC group as well. Is nilpotent FC group, and even more, Z of G1 is isomorphic to Z of. Okay. Firstly, because they have the same set of configuration star by the theorem that I mentioned before, we have f of G1 is exactly the f of G2. It means that they have the same quotient, finite quotients. And on the other hand, G1 is the nilpotent, and I say G2 is nilpotent too. Why? Because we know that there is, in fact, there are some sequences of semi-group laws that a group, a finite group, a group admits in that and satisfies in that law if and only if that group is nilpotent of a special class. So there is a semi-group law something like this. Omega is, for example, eta, a semi-group law, which G elements of G satisfied in this condition holds for elements of G1 because G1 is nilpotent. Therefore, G2 is also nilpotent. It's an equivalent condition for nilpotency with, as I said, a special class of nilpotency. So, because it is if and only if condition, we see that G2 is nilpotent as well. I want to prove that G2 is FC group, and it's easy because since G1 is an FC group, we see that, okay, G over Z of G is finite. So it has of finite order. It means that there exists a positive integer such that for each x in G1, xz of G1 with power n is z of G1. It means that for every y in G1, x and y is yxn. And this equation is exactly a semi-group law. Therefore, it must happen only again for G2 also. So for each P in G2, let me write G, for example. For every G and H in G2, we have G in H is H Gn. And what does it mean? It means that G2 over its center is a periodic group. Because for every x in G2, xn, or for every g, better to write, gn is a member of z of G2, and this group must be periodic, but we know that this group is also nilpotent and finitely generated. On the other hand, there is a problem, there is a theorem that say every, I remind it here, every finitely generated nilpotent torsion group or periodic group is finite. Therefore, we see that it is finitely generated nilpotent torsion group. Therefore, G2 over its center is finite, and therefore G2 is an FC group. We prove that if G1 is nilpotent and FC, then G2 is nilpotent and FC, and we must prove something else. It is that Z of G1 is exactly Z of G2 up to isomorphism. Since they have the same set of finite quotients by the theorem I mentioned, we see that, and because they have the derivation groups with finite order, we see that G1 times Z is isomorphic to G2 times Z, and therefore they have the same centers, Z of G1. And because they are abelian, we can prove that G1 is isomorphic to G2. Z of G1 is isomorphic to Z of G2. And the proof is complete. Okay. And another theorem in this sense, let G be the infinity. I remind the definition again. Let G be the infinite dihedral group, and let CON star of G1 of G is the same as CON star of G2, for example, of H. Then G2H is exactly G, which is the infinity dihedral group by isomorphism. I want to prove this theorem. Before that, I remind the definition of dihedral group. and its properties, and after that I prove the theorem. This group is the group generated by two elements. Which have order 2. These are relations and these are generators. Every element of G has a unique representation. Every element X, for example, of G, uniquely represented by the product of A and B, A, B, A, B. A and B can be omitted. It means that I and J can be 0, and the other powers must be 1. And this is unique. We explained it before in the first session. So we can speak about the length of X, and we saw that we know that everyone knows that the infinity is amenable. Okay, I want to prove that these two groups are isomorphic. For proof, the main point in the statement of the theorem is that they have the same set of configuration star. So I want to find an isomorphism between D infinity and H. Now, suppose that G is this set, the elements generating D infinity, A and B, and suppose that E, the partition, has 5 parts as follows. 2, 1. E1 is only the identity element. Each non-identity element of X has such a representation, and it can be the identity element. E2 be only A, E3 only B, and E4 to be the A, something like omega A, starting with A, of course, except for A itself, and E5 to be omega B, I mean the words beginning by B, except for B itself. It's the partition for the group, and this is a generating set for the group. So after writing the configurations and applying the condition, this is something and can continue to prove. So the configuration corresponding to these G and E are these configurations. Let me write from my notes. It's not difficult to write because these three, the first three subsets are singletons, but I need to write it very let me find it. It must be precise because I want to define an isomorphism. Let me find the infinity. It admits 7 configurations, and okay, let's write. C1 is if you choose identity here after multiplying by A, it is E2, and by B, it is E3. This is C1. C2 is starting with A, multiplying by A, it goes back to E1. By B, it is in E5. Starting with B, by A it goes to E4, and by B it goes to B again, into E5. Okay, it is, no, by B it goes to E1, okay, because the order is 2. Okay, C4, then you start by words starting with A. It can be after multiplying by A. It can be in omega A, so it's 4. And by B it is E5. And again, it can be 4. By A, it can be again 5 and 5. C6 and C7. Let's start with a word in E5. It's starting by B. So multiplying by A, you are going to E4. By B, you may stay here in E5, or go to E4. Okay, 5, 2, 3, 4, 5, 1, 2, 3. You may go to E3 by multiplying by E1. If you have AB after adding this, so 4, 3. If you start with AB, you are in 4. By A, you stay here in 4, and by B, you can go to E3. AB, it is 4, and after that you can go here, and after multiplying by B, you are in E5. And let me check once again. If you are in E5, you can be in this shape. So multiplying by A, you are in E4, and by B, you can go back in E2. I think it's all configurations that we can write. 1, 2, 3, 4. I hope there is no repeated one. 4, 5, 5, 4, 4, 5, 5, 4, 5. Okay, I think that's okay. This system is a system of an amenable group, and as an exercise, you can find non-negative non-zero solution or normalized solution. Find the normalized solution. Let's go back to our proof. Okay. Since CON star of G is CON star of H, then there exists two members generator, something like, for example, X and Y, a generator for the group H, and a partition with 5 parts, F1, F2 to F5, such that CON of G and E is CON of H and F. With these configurations for the group G for D infinity, we know that A2 F1 is F1 E1 for D infinity. I'm saying we know that the order of A is 2, therefore A2 E1 is E1, and B2 E2 E1 is E1, A E1 is E2, B E1 is E3, and we know that for each X in the infinity, there is a unique representation. There are something. There is, for example, M, such that X E1 is A, B, A, with length M, E1. So, because they have the same set of configurations, exactly such equations happen for the group H. Therefore, we have this condition. For the group H, we have X2 F1 is F1, Y2 F1 is F1, and XF1 is F2, YF1 is F2. Because these things are exactly, directly come from the definition of configurations. So because they have the same set of configurations, exactly the same things happen for the group H. And another thing, that for each Z in H, we have ZF1 is X F1, which is unique. Of course, I and j can be 0. Okay, if we prove that F1 only consists the identity element, we prove that D infinity and H are isomorphic. because in this case, H is generated by two elements X and Y with order 2. And every element of Z of H has a unique representation as the product of X and Y's, and it proves that these two groups are isomorphic. So it's remains to prove that F1 consists only of the the identity element. E dot loss of generality, we can assume that F1 contains the identity, because if not, you can multiply the inverse of the elements of F1 to the to your partition and have new partition and new generating set, and what we want is set. Okay. So without loss of generality, suppose that 1, the identity element of H, belongs to F1, and it may contain something else. Maybe F1 minus the identity is not empty. If it is not empty, the proof is not common, the theorem is not satisfied. So we want to prove that this set is empty. So if this, we must go to a contradiction. For this, once again, look at this equality, because configuration of G is configuration of H. We use this side, we choose a configuration here, and after that we find a configuration in H like this, and have some results. Now I want to come back from configuration of H to the configuration set of G, and we see that if F1 is non-empty, define a new partition. L1 is identity element, L2 to be F1 minus the identity element, and Li to be Fi minus 1. So L3 is F2, and so on. Therefore, there exists a new, for example, configuration pair G prime and C prime for D infinity, such that CON of L of H and L is configuration of G prime and T. We don't need prime. And this is for the infinity. By the same argument, we see that the infinity is generated by, if G prime is G1 and G2, we see that the infinity is generated by G1 and G2, and by checking case by case, you see that because these two generate the infinity, and A and B also generate the infinity, we see that case by case, that elements with this shape, A, B, A, B, and every element of D infinity belongs to T 1, T3 to T6, and therefore T2 must be empty. I omit some parts of the proof because I know it's somehow boring. I want just write the conclusion, the main part of the theorem of the proof. And you see that T2 is empty, and it's impossible because T is a partition. So it's a contradiction, and it's because of these assumptions. Therefore, we have F1 is empty. F1 is only consists of the identity element of H, and therefore the infinity, it is sort of clear that the infinity is isomorphic to H, and the proof is complete. So in this case, we also prove that two groups are isomorphic. There are some other theorems in this case, like this. I only choose two of them, one for FC groups and the other for the infinity. And also there are some other theorems. For example, I mentioned one others. For example, if CON of a group, no, not an unknown group. Suppose that it is the Burnside group with n generator and the exponent m, and the configuration of these two groups were the same, then we can prove that n is n prime and m is m prime. Therefore, P of n and m is isomorphic to P of n prime and m prime. It's, of course, configuration of stars, and these are not very complicated. You can see this very easily. For example, we can note about configuration of groups. The title of the paper is that, and you can search it and find the proof of this theorem and many other theorems. Okay, if there is any question, I will answer.